Welcome back to our class. Let's continue our discussion for the key technical challenges to the optical communication in the next decade. We will continue to discuss the last few changes in the development of key technologies in the optical communication network. First, number 7, it is whether optical access network can break through the TDM mechanism and implement the new point-to-multiple point technologies. Currently, the optical access network is in the 10G PON phase and can provide 10G upstream bandwidth and 100 microsecond latency. Services are isolated using different VLANs. 10G PON use the WDM plus TDM mode. WDM is for the upstream and downstream services. Different wavelengths are used to transmit services to avoid conflicts. In TDM mode, the uplink services of different users are transmitted on the same channel and allocated with different time slot. With the promotion of cloud VR and ultra high definition 4K and even 8K video services, we predict that in the next 10 years, the uplink bandwidth requirement for the optical access network may increase to 200 gig per second, and the latency needs to be reduced to 1 microsecond. Services need to support hard isolation. Based on this trend, the current optical access network has encountered some bottlenecks during the evolution towards these goals. The current architecture cannot meet the requirements of 200 gig upstream transmission. 1 microsecond latency and hard isolation is not possible. A new optical access network architecture needs to be found to replace the current TDM architecture. After 10G PON, the PON technology can evolve in two ways. One is to increase the single wavelength rate and increase the baud rate from 10 gig to 25 gig, even to 50 gig without changing the existing solution architecture. The second solution, also called TWDM PON, can use the multi-wavelength overlay mode on the basis of increasing the single wavelength rate. Each wavelength carries a rate of 20 gigabits per second or 50 gigabits per second, and we can use multiple wavelength overlays to 50 gigabits per second or even 200 gigabits per second. The two solutions can only be regarded as extension lines of the original solution and can only meet short and medium-term evolution requirements without any fundamental architectural innovation. For the objective of long-term evolution for the optical access networks, our current research direction in the industry actually focus on the innovative architectures and learning technologies using in wireless networks. For example, multiple access technologies. Like in the wireless, we actually can use OFDMA and OCDMA. So we can learn this multi-access technology from the wireless to improve the network capacity and implement the hard isolation between the different services. The eighth change in the evolution of optical communication, it is related to satellite communication. Can we build high dynamic, large bandwidth, and large-scale satellite communications optical networks? Satellite communication, in fact, it is not a new concept. Back in the 1990s, Motorola spent as much as $3.4 billion on the Iridium program, hoping that it can build a satellite communication network that allowed phone calls from anywhere in the world. This plan was later replaced by a faster and less expensive terrestrial base station network because of its high tariffs and poor signal quality in the Iridium program. After 3 decades, Elon Musk, his Startrain program, plans to launch some more than 12,000 communication satellites into orbit via the SpaceX program to form a network that will provide high-speed internet service to everyone in the world. By 2020, the Star Train program has officially begun operation. Right now, China and Europe has started some similar projects like the Hongyun project. Currently, satellite communication is still in the initial development stage, and its application scenarios are limited. Currently, the bandwidth, networking scale, and lightweight needs to be gradually improved. First, it's the bandwidth problem. Take Musk's StarChain network as an example. The network bandwidth provided by StarChain networks is only 1/1000th of that provided by 5G network, which is very far from the gigabit level. Spatial digital coherence technology is the future development chain of this area. The second one is the networking scale. Take the Star Chain as example again. The satellite communication networking mainly use the chain topology. This cannot meet the high reliability requirements for some high-value services. It is a good idea to introduce the mature ASUN technology in our terrestrial optical network into satellite communication optical networks. Third, the operational life of the satellite in the sky is a very important indicator. Again, it's a Star Chain project. The current life of a single satellite is only 5 years. If we look at the current SpaceX launch speed, maybe before the chain is completed, the first generation of satellite which we launch in the sky will be obsolete already. And you have to keep launching satellites to maintain the network. Lightening of optical communication satellite is definitely a change. Lightening and low power consumption can prolong the working time and life cycle of the satellites. The last challenge is the level of component integration. Can we achieve ultra highly integrated optoelectronic modules? We know that operators have precious equipment room space and have high requirements on energy consumption reduction. Optical network devices are generally deployed in the central equipment room of the backbone network due to their high bandwidth and large capacity. As OTN devices are deployed in CO equipment rooms, the space and power consumption of these equipment rooms are increasing. Optical network devices has always followed Moore's law and become more integrated. In recent years, we have also started to face some challenge in the ultra-high integration chain. For example, can a single optical module output multiple wavelengths and cover all available spectrums? Alternatively, a single wavelength support long-distance transmission with a capacity of more than terabits per second. This poses great challenges to the bandwidth and linearity of the optoelectronic devices. In addition, the problem of interchannel crosstalk caused by improved integration must be resolved. Last but not least, a low-carbon society has increasingly high requirements on operators' energy consumption. The power consumption also need to be considered and need to be reduced. In the next decade, optical communication devices will continue to evolve along the chain of miniaturization, high integration, and low power consumption. At present, the industry mainly focuses on packaging integration technology, photonic integration, and optoelectronic integration. Lastly, let's make a brief summary. In this chapter, we introduce several other chains in optical communication, including optical access networks, satellite optical communication networks, and improving optoelectronic integration. The optical access network has two evolution approaches. One is to continuously evolve from 10G PON to 50G PON, and from 2 wavelengths for upstream and downstream to 4 and even 8 wavelengths. Another direction is to adopt new architecture, for example, OFDMA, OCDMA. Satellite optical communication networks are evolving towards higher bandwidth, larger networking scale, and low cost and lightweight networks. The ultra-high integration of components is the last change in the evolution of optical communication networks. That's what we have covered in this section. Next, let's use two simple questions to consolidate the contents. First, it's a single choice question. Which of the following statement about the optical access network is incorrect? Option A, B, and D are all correct. Option C. Currently, the optical access network uses two different channels in the upstream and downstream direction, and the future evolution direction is to upgrade to 4 or 8 channels. So the answer should be C. We don't have 20, 40, or 80 wavelength. That's already the DWDM solution. The second question is a multi-choice question. Which of the following are the development chain of satellite optical communication technology? A. Large bandwidth. B. Large scale networking. C. Lightweight and low cost. D. Ultra large scale access. Large bandwidth, large scale networking, lightweight, and low cost. They are correct. So A, B, C is correct. But D is incorrect. So we only select A, B, C. Well, that's all for this topic. Thank you.